Okay, so a couple of questions, linear equations versus quadratic equations, and how do we write quadratic equations? Now, first of all, what I would like to say is that we don't just make up functions. We, by people, we humans, we do not just make up functions or equations. We usually, if we have a linear equation or a quadratic or exponential or logarithmic or all kinds, yes, what we are trying to do, we are trying to solve a problem. Yeah? So, with that in mind, we have this universe of functions. Some are lines, some are quadratics, some are cubic, some are exponential, some are logarithmic, some are constant. So we have this universe, right? They exist, right? They exist already. But the question now is, when and how do we use them? So I'll use an example of equations that were used in module 4, right? So this is how cost was modeled. That's what in the module 1 review, that's what the equation that was used for cost. This was not just randomly picked. It was picked because with these numbers, with this form of the equation, we are trying to tell a story about how cost works in a particular situation. So, for example, what this equation looks like, right? It's a line, yeah? It's a line that it intercepts the y-axis at 1,000. It intersects at 1,000, and it's increasing. And the slope of this is 40. All of these points are important. Why? It means that what the author was trying to say, it was trying to say that when x equals 0, then the cost is 1,000. Right? So let's say I need to buy some sort of very special diamond. Yeah, I'm getting engaged and my girlfriend needs a special kind of diamond. Well, before I even start to shop or buy diamonds or look at diamonds, there's a fixed cost. This is the money that I already have to buy. Let's say these special diamonds or rings or something, they only exist in India. So then I have to spend $1,000 just to get to these diamonds. So in order for me to write an equation to describe that situation, I need an equation that has a fixed cost of 1,000. Yeah? Now, I need something else. I need to say that for each gram or milligram of whatever diamond right? For every carat of this stone is an extra $40. Yeah, every carat of this stone is an extra $40. So I want more carats. I should pay for each carat. I pay an extra $40. So then that means that I also want an equation with a slope equals 40. Now, is this equation linear? Meaning for each extra carat I pay the same amount, a constant? Well, then I need a line. That's why this is constant. On the other hand, sometimes I may need a different type of situation. And let me use this is another equation that was given in the module. So the thing is, every time I introduce an x squared, right? So this is one type of quadratic, but x squared, just x squared. So r of x equal x squared. That's a quadratic by itself. X squared minus 2x. That's a quadratic by itself. Just as long as I have an x squared term in there, that's a quadratic. And every time I have an x squared terms, what happens is the graph and the way the function behaves changes. Now it's not a line anymore. Now, let's say if I look at r of x equal x squared, this graph looks like this. Yeah? So this graph describes a situation where as x, right, r of x, as x increases, something happens, something different happens. First, the revenue decreases and then increases. But how does it increase and decrease? See, the rate of increasing is not constant, right? A constant would be something like this, right? The rate keeps accelerating, right? See how this line gets higher and higher and faster. So, when I want to describe a situation where revenue increases with the value of x, but as x gets higher, the revenue rate of increasing accelerates, well, then I need a quadratic. So anyway, the idea that I'm trying to get here is functions are tools that we use to describe reality. We need a constant rate, that's a line. We need an accelerating rate, that's a quadratic.